So we're back for the second half week of the TMD Winter School. Duff Neill will continue to teach us about EFTs and perhaps how they connect to TMDs. So take it away.
Yeah, so actually, we'll probably get fairly deep into TMDs today, because I covered more ground than I thought I was going to. But just to recap, what were the major points? Well, when we were thinking about EFTs, we wanted to think about our degrees of freedom. We wanted to think about the symmetries that degrees of freedom obeyed. Then 3, we wanted to think about power counting. And encoded in power counting is some sort of state of affairs that we're only considering weak perturbations around that state of affairs. And by weak, I don't mean that like their coupling is weak. Their coupling could be strong. It's just the fluctuations don't move you very far away from whatever is the state of affairs that you want to live in. When we did this, we found various objects for hard scattering. We had our B in perp mu, which was our leading power field operator for gluons. We found various soft Wilson lines. And finally, we also found quark fields. I'll go ahead and write down their definition here. At W in dagger. I probably forgot to do this. Psi of x, but this is some creation and annihilation operator for your quark fields. And I'm projecting out the large components of it. So the leading order components. And that's where that in bar slash comes from. Finally, we had our power counting for our collinear derivatives. Which just means that if I act on a collinear operator, these derivatives will move you down by order lambda or order lambda squared. This one we could actually eliminate for just a normal partial derivative via our Wilson lines that we constructed. And once we eliminated them for these normal derivatives via the Wilson lines, then we could argue that all such derivatives in that particular direction acting on our collinear sector can be absorbed up into the matching coefficient. And so we didn't have to worry about these things being a potentially order 1 in the power counting. I guess I should make the dimensions correct. So this would be like times Q, times Q, times Q, where Q is some energy scale that typifies our collinear sector. Then we talked briefly at the very end about the power counting for softs. Should be something Q times order lambda dA. And traditionally in SCET, if A equals 1, we call this SCET2. If A equals 2, we call this SCET1. Now you might think that's horribly confusing names. You can thank people who do B physics for that, because when you do B physics, the first theory that was constructed was SCET1, and then the second theory that was constructed was SCET2 back in the B physics days. And there was even a sequence of matching where you would go from SCET1 to SCET2. So it made sense then. After that, it never made any sense. And no one does B physics anymore. That's not true. People do B physics. But a lot of people have moved away from B physics, so the history of that's been lost. So lambda, which is much, much less than 1, is our power counting parameter. And it controls how far away we can go from the ground, from our ground state. And as lambda gets too large, then your EFT will break down because your exciting degrees of freedom that don't properly belong to your EFT. So there's going to be 2 points that we haven't really addressed yet. In SCET, what actually fixes lambda? And then the next point, and I'll even do this as 4 because it really should be in the list that I wrote up before, which is the ultimate logical conclusion of power counting. And this will be sort of the main topic for today. I'll even write that out because it's important. Something called the multipole expansion. And it's called multipole expansion because the ideas behind this particular procedure were first fleshed out in our QCD. And that term multipole expansion makes a lot more sense in our QCD because you're actually legitimately doing a multipole expansion as we would have learned in E&M back when you read Jackson chapter 3, maybe. It was invented and applied to in our QCD by Grinstein. I forget the exact number for this paper, Grinstein. I'm probably misspelling both of their names, and Rothstein. And it's probably the most overused word in effective field theory literature, and no one ever cites this paper. It's kind of sad. If everybody actually cited that paper whenever they use the term multipole expansion for effective field theories, that paper would have so many more citations than it does. It's a travesty. All right. So lambda is fixed by the observable. So for instance, since this is TMD school, I'll illustrate everything using the Drellian transverse momentum spectrum. So suppose, for instance, we have PP goes to L plus, L minus, plus X. And I'm interested in the momentum of this Drellian pair. So what do we observe? Well, we observe a couple of things. One, since we prepared the initial state, we know what the initial state momenta are. These are light-like vectors because we'll pretend that our protons are massless. We're going that quickly. These are light-like vectors along the n and the n bar direction, and roughly speaking, you can think that n is something like square root of s mu over t here, and nothing else. And bar square root of s and mu over t. So we observe that because we prepare it. But in the final state, what do we measure? Well, if we break up the total momentum of the Drellian pair, so Q equals PL minus plus P plus, then we would observe, say, its rapidity and its transverse momentum. where this is the n-bar.q, this is the n.q, and this is all the PERT components in my light cone coordinates. My light cone coordinates are just set by the initial state that I prepared. And so if I draw a nice picture, and Chris wanted me to do things in color. So there's a fire, oh, it's a terrible color. We'll just do things in black and white.
Click on the same pen icon again. The other one was the highlighter.
Oh,
doesn't look that
oh,
good.
this one?
Just click the pen. Yeah, there you go.
Oh.
There you go.
Leftons are always blue. Here we go. And of course, they recoil against QCD stuff. So I'll put it here. So that would be my plus X, all that green stuff that they're recoiling against. So there's our physical situation. Now, assume it's much, much less than Q, and this will set our power counting parameter. So whenever we're doing an expansion in our effective field theory, we should always think of it as an expansion as QT over Q. Now, the initial state that I prepared had no transverse momentum associated with it. So the protons have no net transverse momentum. Their internal constituents, of course, can, but they don't. So that means the transverse momentum of my Drell-Yan pair is just the opposite of all the QCD stuff in the final state. And since this quantity right here is of order Q lambda, that means everything on this side of the sum generically should be order Q lambda. Just so that both sides of the equation are the same order as each other. Or they could be order of Q lambda or smaller. Now you could say, oh, but Duff, what if you had like some back-to-back jet in the central region? Those could both have very high transverse momenta, balance each other and sum to zero. Yes, this can happen, but it's subdominant. I'm not necessarily going to go through the argument for that. It's in a paper of mine. And I think it's in several other papers. But you can write down the Feynman diagrams that contribute to this particular configuration and show that those Feynman diagrams are subleading in the QT over Q expansion. So I'm not going to dwell on that. Suffice it to say, I'll just invoke an authority right now and say, yes, these are subdominant. So in general, you're dominated by configurations where everything in that sum is of order Q lambda or smaller. We're in Drell-Yan. We're doing Drell-Yan. Why do I say final state hadrons? Thank you. Right, is that better? Okay. What was that? So now we have to think about the types of final state radiation that can enter that sum that can go on shell as lambda goes to 0. And why am I concerned about this? Because if lambda was absolutely 0, right, I'd be in my Born configuration. Right? If lambda was absolutely 0 in Drell-Yan, I would have a Q and a Q bar. They would annihilate each other. They would only form my Drell-Yan pair. This is a photon. Here's my cut. And this would be my cross section, my Born configuration. And if lambda was absolutely 0, then Q and Q bar are both on shell coming out of the initial state. And there's no additional radiation anywhere. So there is no QT. So lambda goes to 0 approaches my Born configuration. It's the state of affairs which I wish to preserve. It's my ground state. And I actually wish to obtain a real ground state in some sense. And that's why I demand that everything in the final state be on shell as lambda goes to 0. Now, there's a more deeper principle here, which is EFTs are built only from on-shell degrees of freedom. Which means a degree of freedom which is has an on-shell dispersion relation as your power quantity parameter goes to 0. This gets complicated in both NRQCD and SCET, respectively, because of things called Coulomb gluons. And there's a proper way to handle this, which is to integrate them out and make a potential. But we're not going to get into that unless we have time at the very, very, very end of the talk. So we'll have soft and collinear degrees of freedom. I want them to be able to scale on shell, which means that whatever p squared is, it has to go like q squared times lambda to some power that's not 0, so that when lambda goes to 0, p squared goes to 0. Because my on-shell degrees of freedom are all partons, so they have a very nice dispersion relation. Lambda. These will be my degrees of freedom to construct my effective field theory from. Power counting that they'll obey. Now, there's a couple of things to note here. One, they all have the same transverse momenta order, which is good. They have to all enter into that sum over the final state, where that sum has to be of order q times lambda. Therefore, the transverse momenta of all of these guys better be q times lambda. But schematically, QT is going to be the P collinear perp plus the P collinear bar perp plus any P soft perp. This is order Q times lambda, so these must be order Q times lambda. The other important thing is that if I break up any of these guys, so it could be collinear, collinear bar, soft. If I break them up into my light cone momenta, both of these terms are order lambda squared, which means there's nothing to expand, right? And this is important because if I have a genuine delta function sitting around somewhere, and I'm actually going to make these guys on shell in the course of some computation. If I had to expand either one of these terms, then I would no longer be able to satisfy this delta function. In other words, I would no longer be able to get that momentum to genuinely go on shell in the course of my calculation. I would get nonsense if I expanded out the perp because it was too small. Then one of the light cone components would just be 0. And now what am I talking about? Talking about some weird mode that's not actually on shell because I can't really fulfill this delta function. So that's why it's important that these light cone momenta don't get expanded. That you have homogeneous power counting within each one of the sectors. Now, between the sectors, you don't have homogeneous power counting. Things can be expanded. In particular, if I have a P soft plus a P collinear, this is not homogeneous. But any such combination is going to be absorbed into some iconal propagator, which we argued, I think, last time. And then the last reality check that we have to do is that if I sum over everybody, this, of course, is of order Q squared. Where in the course of all of this discussion, this Q squared was the Q squared of the Drell-Yan pair, right? So we put flesh on what that energy scale actually is. It's the large invariant mass of the Drell-Yan pair. And this is important because the collinear radiation out of the initial state coming from one proton and coming from the other proton have to sum together to a large enough invariant mass in order to have actually generated that Drell-Yan pair in the course of the collision. So this is another important constraint. What happened? There we go. So these are all the ingredients of my effective field theory. Now we have to shift gears just a little bit and ask, what is cross-section in full QCD? Why are we switching gears? Because after we answer that, we'll then match to SCET, multipole expand. And then we'll get our factorized cross-section. So the cross-section in full QCD will sum over all possible configurations of the final state momenta. We have our initial states. We're going to probe the electromagnetic current And then we'll have the other side of the diagrams. And of course, all of this is going to be contracted up into the lepton tensor. So this tensor just describes what the leptons go off and do in the course of their merry way after being created. J is the electromagnetic current. I have to actually create these lepton pair, and that's actually just QCD probing the electromagnetic current. And then I have my initial states. And note everything here is happening at amplitude squared, because that's where observables live. So earlier I talked about amplitudes, and when I talked about amplitudes, I didn't really have to worry about my power counting parameter. As long as I assumed that I had one, then I could just do some sort of expansion, and I got some sort of two-jet operator out that we talked about last time. And I couldn't say too much more about that two-jet operator. Because amplitudes aren't observable, so nothing was actually constraining what that lambda would be when I was doing the expansion at the level of amplitudes. Here, what's constraining me is what I've observed. I've observed the fact that my PP collided together. They excited the electromagnetic current to form this Drellian pair. And I measured that transverse momenta. And here I just squared things up, and I'm summing over all possible final state configurations consistent with what I had observed. So it's a cross section, genuinely observable. So J hat is my electromagnetic current. In full QCD, you might write something like this. I sum over all possible flavors. Here are my quark fields. They're gonna have some charge associated with them. Like so. And gamma is my direct structure. So as QT goes to 0, we know that we're going to be in some sense in a two-jet limit. All I could write down that was consistent with my Q squared large, QT going to 0, that's on shell, is my collinear modes along one of the proton's directions, my collinear modes along the other proton's direction, and then my soft radiation, which could be anywhere. Remember, it has lambda, lambda, lambda scaling, so it's isotropic. All of them have just the right order in the transverse momenta such that I can balance out this particular conservation equation down below. Yes, minus sign there. So that immediately tells me, since I have two collinear sectors and one soft sector, I should be matching my QCD current onto an SCET current formed from two-jet operators. Now, we talked about how to form these two-jet operators last time, so I'm just going to write down what the answer is because we all should know what to do. There will be a matching coefficient, because there always should be a matching coefficient. In Wilsonian language, this would be all the modes that I'm integrating out. So this would be all of the hard dynamics that actually created the Drell-Yan pair. So if I have my full QCD diagram, it has all sorts of exchanges and radiation coming off of it. All these loops that are occurring, and note I only care about the loops here. I don't care about the final state radiation. Those actually have to be part of my effective theory because I've constrained all of my final state radiation. So all of these loops here, all of these virtual loops, when that virtual loop momenta Q squared goes to infinity, the contribution that has to my process is going to go into my matching coefficient. Thus, my matching coefficient can depend upon the sum of the momenta of P collinear plus P collinear bar plus P softs. Why? Because this entire quantity right here is of order Q squared. So everything in that matching coefficient is of order Q squared. So that's great. I have fermions that create my Drell-Yan pair. So I'll have fermionic jet operators. Then I have my Wilson lines. Now, there's something troubling about this expression that I just wrote up, or at least there should be something that troubles everyone here. And that this thing is not homogeneous in my power count, as I've written it. Why is it not homogeneous in my power count? Well, the sum of the momenta inside my hard matching coefficient, right, has momenta in it that are not all order Q. There's also order lambda momenta in it. There's also order lambda squared momenta sitting inside this sum. Inside this exponential that I've written up, there is order Q, order lambda, and order lambda squared momenta all sitting there. And it's not homogeneous in these sums. That's bad. Now, this was the most general thing I could have possibly written down. That's 2-jet. That was constructed from my leading power fields. But it's still itself not leading power. I know it's the most general that I could write down because we figured out last time what my leading power fields would be for both the soft sectors and the collinear sectors. We constructed them to obey all the particular symmetries. We know we have to use 2-jet operators because of the power counting that I've assigned to final state and the fact that I only have a 2-jet configuration where the jets are the QCD radiation going up and down the beam. So all I've really done here is I said, you know, I have one collinear operator. This is its total momenta that it's interpolating, my P collinear. I have another collinear operator, it's interpolating some total momenta for P collinear bar. And I have all my soft radiation interpolating their soft radiation. And of course, by momentum conservation, I know that all of this has to connect back to whatever my total hard radiation is. And so here, when I write this statement up, I'm basically just saying all the momenta in my effective field theory sectors sort of better sum up and contribute to the momenta of my full process. In other words, I matched my current. But I've done it in such a way that's not homogeneous. How do I get to homogeneity? This is the multipole expansion. In other words, I need to use my light cone momenta in bar and perp. I need to break up in the places where I see sums over multiple sectors of my momenta, break those sums up into my light cone components, and then drop parts of those sums which are subleading. So for instance, when I do P collinear plus P collinear bar, with P soft in there also, what should this become? Well, this should just be P in bar collinear divided by 2 in when I perform this particular expansion and drop all other terms, now I have homogeneous power counting. This term right here is order Q. This term over here is order Q. And everything else is a power correction. So inside this matching coefficient up here, where I wrote down the total sum of the momenta that could feed into that hard matching coefficient, I really only care about the large light cone components of my 2 collinear sectors feeding into that hard interaction region. The next thing I have to multipole expand is what's in my Fourier transform exponent. This is going to be a little more complicated. There'll be terms which are associated with the n bar dot z direction, conjugate to the n bar dot b collinear plus n dot. For instance, now, this is homogeneous already, so we're happy. Every term here is order lambda, 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 lambda. This is order lambda, this is order 1, this is order lambda squared. So I kill these. This is order 1, this is order lambda squared, this is order lambda. So those drop out. This is the expansion I'm doing to the operator that I wrote up earlier. And then when I'm done doing that, I can now write down my multipole expanded current matching. Note, once I expand out certain components of the momenta, I can actually perform those integrals because I have delta functions here. So they'll become unconstrained. They'll just move down to the particular sector that they like to live in, and they'll just get killed by doing that delta function. So there is my Fourier transform exponent, properly multipole expanded. And now finally I have to put in all of my operators. Yep.
In the expression, in the first dimension,
Where?
just the first,
Very first line.
integral b and bar. Just j means equals to.
Here's my z's.
That's a j means
First integral.
equals to integral b.
He wants the integration measure to look right.
I see what I did. Yes, you're right. I see.
Also, the third line here. This is that and so the n bar dot zero in the experiment. That n dot pc is that n dot pc.
That's nbar.pc.
No, in the second one.
Yep, you're right. That should be barred.
You have a tough audience.
No, he wants things to be correct, and I admire that. So now, after I've done this multipole expansion, the matching of my full QCD current onto my SCET current all has homogeneous power. So this is just but the first term and some power expansion. There'd be both subleading power operators, and there'd be terms associated with this multipole expansion, which would actually appear as derivatives operating on those subleading operators, right? Those derivatives operating on my subleading operators. How do I get subleading operators? I take derivatives. Where are those derivatives coming from? The derivatives are coming from the fact that I've expanded out these momenta. Momenta correspond to derivatives. So it all makes sense. Those derivatives that you would write down for those subleading operators are coming from somewhere. They're coming from the fact that I'm expanding out these momentum components. Now, this is a very large expression. It takes up my entire screen. But what do I want to do? I want to take this very large expression that takes up my entire screen and just substitute it into that cross section that I wrote up earlier. Right. Now, I'm not going to actually do that. I'm just going to write out what happens when you do that. The thing that we were interested in is this correlator. everyone should know that that's just all the perp of my various p-soft, p-collinear EZ. I will break up my total sum over all possible final state momenta into a sum over all possible collinear configurations, all possible collinear bar configurations, and all possible soft configurations. Why am I allowed to do that? Well, because my observable constraint that QT goes to 0 automatically selects out that all possible momentum configurations have to be either collinear bar, or soft. So I'm allowed to break this sum over all possible X into a sum over all possible collinear, all possible anti-collinear, all possible soft. There is no initial state soft radiation. There's only collinear initial state radiation. Why? Because I'm all powerful and that's the way I prepared the world. I actually don't have a much better answer. I guess if you get into small x physics, you might actually have an argument about whether or not there is soft radiation in the initial state or something, but for our purposes and for our power counting, we can make that assumption, and that assumption is self-consistent. So there's also a fierce thing that you should do to get rid of that gamma mu, gamma nu that would have appeared on either side. And I guess to make that plainly obvious, I'll put in a here, so that all my Lorentz indices are contracted up. But all that L mu nu would do at leading power is give me some G mu nu, and that'll allow me to do my fierce thing. This should be collinear, collinear, collinear bar, soft, soft. Now, I didn't go through this exercise. But when I substitute, I have all these delta functions here, right? And I have to substitute the current in on both sides. You can actually go through the exercise of what's going to happen. Well, since this state here and this state here has the same momenta as that state there and that state there, those other delta functions which would have integral primes associated with them would just get set to the momenta of these states, which are also constrained by these delta functions on this side of the cut, so to speak. And that would just enable me to go and do all of those intervals. So I didn't put them in there, but you can go through the exercise and convince yourself that, yes, I evaluate this at 0, gets rid of this exponential entirely. And then because of the states down below, I can get rid of all of these delta functions that would have appeared with these operators here. And so I only care about the delta functions on this side. Now that looks like a horrible expression, but it's homogeneous in power counting. It's doing kind of what we expected it to do. I have some hard matching coefficient up here that's describing how my quark and anti-quark meet each other to excite the electromagnetic current. It injects the right amount of momenta into the electromagnetic current. Oh, and I forgot one last thing. I'm so silly. Oh, no, I know, I'm fine. So on this side up here, I didn't have my interval over IQ yet, but I have to put that in. That goes, so the hard matching coefficient describes how all the hard modes and whatnot that actually interact with both in and in bar go to form my electromagnetic current. And now I have these beam operators and this soft function, and everything is homogeneous in power count. In other words, they're only sharing momentum components that are the same. There is no momentum exchange between my soft sector and my collinear sectors in the light cone components, because that would have been subleading any such exchange. And there is no momentum exchange between my two collinear sectors in their small light cone component, because that would have been subleading. And Multipole expanded all of that out. So everything is homogeneous in power counting in this particular expression. So you might think that we're done. And it's 9:57. So that took way longer than I thought it was going to. But we're not. Everything above is naive. Why do I say everything above is naive? Well, so far, the only thing that's actually defined for me the scaling of my modes has been the multipole expansion. The fact that I expanded the cross-section according to the power counting that I assigned those modes. These operators that I wrote down, my Cayenne bar, my Wilson lines, when we initially derived them on Saturday, we derived them from an arbitrary power counting parameter, right? I would have gotten the exact same operators for any lambda. And I would have gotten the exact same operators for any power counting that I would have assigned to the soft sector. It was not until I had performed the multipole expansion on the momentum convolutions that I actually now have given these operators any sort of knowledge about what their scaling is. Because I've done the multipole expansion and given these operators identity, given them meaning in life, because multipole gives operators meaning and purpose, and sort of we'll keep personifying them knowledge of their scaling. What else is it going to do? It's going to induce divergences associated with the boundaries between modes. Multipole expansion will induce divergences. This is a good thing. This is exactly what you want to have happen. The multiple expansion at the level of the operator is specifying that this operator now interpolates modes of this particular scaling. When I do loop integrals, I'm going to be integrating, because I don't like using Wilsonian physics, I'll be integrating over all possible momentum in all of my loop integrals in every single sector, which means that my naive loop integrals in every single sector is going to range over the momentum scaling of the other sectors. However, because I did my multiple expansion, when they go into those bad regions, they'll actually diverge. I'll get an infinity there, which is actually something I want. I want an infinity there because my mode doesn't belong there.
So rather than seeing it as a mistake, it's an indicator that it's non-physical.
It is, well, why do I ever want divergences? I want divergences so I can renormalize them and have an RG equation. And RG equations are wonderful things. They read some logs for you. Right. That's why ultimately I don't view this as a mistake. The multiple expansion induces divergences. The divergences then get regulated. And then after regularization, they get renormalized. And after they get renormalized, they get the logarithms associated with those boundaries are now resummed, which is what I want. In particular, what are the logarithms that I'm going to be resumming? Well, there's going to be logarithms of my hard scale associated with my interaction over QT squared. And there will also be logarithms of QT associated with the large light cone component of my anti-collinear sector, and also a logarithm of my collinear sector, its large light cone component over my QT scale. And we can see this by drawing a nice little diagram. In my light cone components. My anti-collinear sector, C bar, lives down here. So it has a very large light cone component. My collinear sector lives over here. And my soft sector lives right here at the scale QT. So I have to be able to draw some boundary here between these two. That's giving me the logarithm between n bar dot p and QT, this boundary that I draw. There has to be a boundary over here for these nodes. That's associated with the logarithm of QT n bar dot p. And finally, there's the logarithms associated with the fact that my entire effective theory is displaced from my highly virtual modes that were sitting at Q, Q, and Q. They were all virtual. None of those went on shell. All they did was create a Drellian pair. And so this distance will give me a logarithm, and the fact that there has to be some boundary associated with here. So each boundary large log. Each one of those logs is going to be associated with a divergence. That a divergence was induced by the multipole expansion. Normalizing that divergence will therefore give me my evolution. So I don't view this, I mean, sometimes Collins will say, oh, we've done something terrible. Because we have this weird divergence that popped up, the rapidity divergence, for instance. Actually, I don't think this is something terrible at all. This is something wonderful. It's an opportunity to resum logs. Right.
When does he say it's terrible?
I've never understood that statement.
I mean, because he derives his.
I know, he derives everything. He does everything correctly. I mean, don't get me wrong, Colin's brilliant, so he does everything correctly. But because he didn't start using the words like unphysical and whatnot.
Mhm.
And because, but I don't know. I mean, this is a very old story, the idea that divergences induces RGs that then allows you to resum things. I mean, that goes back to Wilson. So,
Probably earlier than that.
yeah. But then again, Collins, if you ever talk to him, doesn't really like Wilsonian thinking. Because you can't, it's too fuzzy for him. You have a question?
Yeah, so earlier when we were talking about making sure that everything is homogeneous, there are different levels of homogeneous, some are 1, some are lambda, right? And so in a sense, you sort of can predict where these different regions are going to be, right? So you know ahead of time that they're not going to be at the same level, so you should have these differences at the boundary. So you're almost, if you do everything right as you're doing it, you sort of get a sense of what's coming.
Yes, exactly.
Okay.
Exactly. Yeah, I
Because when you say
purposely
homogeneous, you're not saying the whole thing is like just a chunk, each of those algebraic equations essentially has to be homogeneous.
Yeah, and wherever they meet, right? So in the transverse exchange, they meet, so that needs to be homogeneous. And I drew this also as a hyperbola because I wanted to demand that n dot p and r dot p is all of order q squared lambda squared, right? Because that was my on-shell power counting system, so to speak. So all of these guys sit on the same on-shell hyperbola. They all have the same relative off-shellness.
That distance that you draw
between
like the QQQ, and then you're saying they're sort of all roughly just as far away.
Now we need to regulate our theory. How much more time do I have?
25 minutes.
Okay, then I might actually do it somewhere. We need to regulate our theory. And since we're going to be doing loop diagrams, the first regulator we will have is a dimensional regularization. And that's because it's the easiest regulator to use in any loop diagram. So my 4 will go to 4 minus 2 epsilon, which equals d. But we can ask, what does dimensional regularization break? What do I mean by break? It breaks a particular symmetry, dilatations. That's actually good for us. Because it breaks dilatations, that means dimensional regularization knows whether you're sitting on this hyperbola or whether you're sitting up at this dot right here. In a theory that was conformally invariant, had a conformally invariant integral that I was doing, there'd be no way in that integral to know at what scale I'm doing that integral because it is conformally invariant by definition, right? But I've assigned a certain off-shellness to these modes down here, and I've assigned a particular off-shellness between these modes up here. I want to break the fact, or I want to be able to distinguish the fact that certain modes are hard and they're up here, and certain modes are in my effective theory and they're down there. So I need a regularization procedure that is sensitive to the scaling that I assigned them. In other words, it breaks dilatations. It's sensitive to the fact that I'm assigning a p squared a particular lambda squared. So I can use dimensional regularization instead of any particular hard cutoff procedure And with that, distinguish between all my modes sitting down in my effective theory in a particular loop integral and parts of the loop integral that go up into the UV. That's what dimensional regularization will allow me to do. What will dimensional regularization not allow me to do? It will never distinguish anything on this hyperbola because dimensional regularization does not break boosts. It's boost invariant. So there's no way for dimensional regularization to ever know where on this hyperbola I want my node to sit. So to fully regulate, I will need an additional regulator. And like I said, I can expect this from just this picture right here. I have to be able to distinguish when I'm doing my loop integrals between the different modes of my theory.
It's actually soft to collinear.
Whether it's actually
this
soft or
case, right?
Yes.
So when you use your pen to show us things, we can't see what you're doing.
I'm so used to it.
I know.
I'm so used to writing on a black.
You can do it if you make a dot, right? But if you just tap it, we don't see anything,
I see.
right?
Just so you know, or maybe you can highlight a little thing and then talk about the
Or like,
highlights.
when you want to, you can underline the word or the thing.
I'm sort of lucky because I can
So I
watch
should
your
like
actual
just turn
board.
You
around.
probably
Yeah.
should have said that an hour ago, but
You probably should. I'm sorry. Man, you guys.
I have a
stoic.
wireless mouse you can like point at.
Stoic. Anyhow. So I'll gesticulate wildly.
Yeah, that'll work. He's giving you a laser pointer.
But then
I prefer laser pointers. My writing is beautiful.
don't point it. Zoom won't see the laser pointer though, right? So why don't we use that on the notebook? You can point with the bus.
Yeah.
Like this?
Yes.
Yeah.
Oh my goodness. I'm such a Luddite. I don't know any of this. Okay, completely lost my train of thought. Okay. So yeah, I need something to break my boosts, right, up and down here. So I'll need an additional regulator. And in fact, the number of regulators that I'll need can be completely deduced from this particular diagram that I've written down. If my soft modes had been ultra soft modes, then the ultra soft modes actually would have sat down here on a completely different hyperbola. Right there. And whenever you do SCET with collinears and ultra softs and no softs, then all you need is dim-reg. You don't need any other additional regulator. Dim-reg differentiates ultra softs from collinears from.
Because they're all dilatations from each other.
They're all dilatations from each other. So it's only in this special case when I'm in SCET2 that I'll need some sort of rapidity regulator.
And that's when it's lambda 1 with a CE2, right?
Yes.
Okay.
Lambda 1 is SCET2. So let's write down my factorized cross section now. I can go and I can do my Z integral, right? There'll be some overall normalization. There's going to be a hard function, which depends on the light cone components of my Drellian pair. When I do that Z integral, I'm integrating, I'm going to do Z.Q. When I do that, and it interacts with this expression right here, right? You can see that n_bar.q is going to set this particular collinear momentum. N.q is going to set this particular collinear momentum. And then the perks are all going to be set down to the Q perk. So I have some hard function. We'll write it as B perp because that's what's normally done, even though I started with Z above. B perp. And we'll have three different functions. I'll explain what this zero is in just a moment. These would be my beam functions. This is what we would call them in SCT. I am not calling them TMD PDFs because when people form TMD PDFs, they like to break up the soft function and fold them into the beam functions, right? So I'll just call them beam functions right now. I'm going to keep soft and collinear distinct because it'll be more obvious how to resum logs if I keep soft and collinear distinct. Hard function. Soft. Now, what are the actual definitions of these particular functions? I'm going to jump out of order. I just give it for the soft function. These zeros here are associated with moment, the component of the momenta that I multiple expanded, right? In other words, here I did a multiple expansion on the small component of the momentum. So once upon a time, sitting here, there was an n dot p collinear minus I n dot derivative, right? But because I did the multiple expansion up in this exponent, I was able to move that derivative down here and kill this object, right? So I could have left that Fourier component there, right? Left it in position space. And then just send that position space variable to 0. That would perform the multiple expansion. It's easiest to see in the soft function, in the sense that I can write it out more clearly there. The definition of my soft function, which is completely in position space, just keep writing as derivatives, I guess, because I've always written the momentum operator as derivatives. Like so. In my fully differential soft function, right, it can have a position space dependence in both the n bar dot b and the n dot b directions. But when I perform multiple expansion, these get set to 0. Now, where are the divergences that I was talking about earlier? Well, this will be a set of loop diagrams. Like so. And if you work out what those loop diagrams are at this particular order, it's just this. The virtual diagrams are scaleless, so they're 0. If you're not familiar with the fact that a scaleless regulated interval is 0, then read chapter 4 of Collins's book on renormalization. He has a very nice argument about why you set scaleless intervals to 0. In dimensional regularization. So these guys are scaleless in dimensional regularization, and they're 0. So here I'm just summing over the contribution of the 2 real exchanges. I've drawn in my Wilson line, so that's like my in Wilson line. This is my in bar Wilson line, in bar, right? The cut right here is just this complete sum over states. So whenever you see the cut propagator, that means I'm actually inserting some term in my complete sum over states. Since I'm doing this in perturbation theory, I only insert in one state for my first order perturbative expansion. I get this expression right here. Now p squared is n dot p in bar dot p minus p perp squared, right? That means I can do this delta function. This expression right here is going to get set to my p perp squared, and I'll be left with 2 intervals. Sorry. So I've set the light cone components of my n bar dot b and my n dot b to 0. I have my b perp component still. This operator here acts on this particular state, so it's going to pick up the perp component. You guys can't see, sorry. These are being set to 0. Here, this operator is going to act on this state and pick up its momentum. So only the perp components, right, are going to be picked up. So that's where this exponential is coming from. It's coming from this constraint on my final state. You can now see the origin of my divergence. This integral is nice and regulated because I'm in dimensional regularization. So you need not worry about this 1 over p perp squared. I can just change my space-time dimensions until the p perps in my measure cancel out the p perps that are down below. Everything's nice and regulated there. I can perform that integral. But here, there is no regularization procedure. And in fact, if we trace the origin of where this divergence comes from, it's from my multipole expansion, because I set these 2 guys right here equal to 0. Now, in the literature, there's been all sorts of proposals to deal with this. There's been Collins 1 axial gauge. Collins 2 space-like Wilson lines. There's been, I think G had one for time-like. Because if I make this guy a space-like Wilson line, I'll deform this, and you can show that you actually will avoid poles. Because components of this vector right here, my iconal line, will actually mix into the perp. And that actually will give you a regularization procedure. It's all very complicated. There's Becker and Neubert 1 and 2. Everybody seems to do 2. We'll just call that analytic. There's did I spell this? Okay, I spelled it right. Yes. Schemimi slash monohar. The delta regulators. Roughly speaking, you can think of this as an iconal mass term. Very roughly. And so even with Schemimi, there's Schemimi 1 and 2. Both are delta regulators. It's like everybody who comes up with a regulator initially realizes that their first regulator they came up with had a problem with it. So they came up with a slight modification of the exact same regulator to get around that problem. This has happened to everybody who's written more than one paper on TMD physics.
Don't you have 3?
Do I have 3? I thought I only had 2. Then there's Duff and Friends. 1. And then there's Duff and Friends 2. Non-overlapping friends. And this is also an analytic style. And this one's the best. All right. Biased here, of course. But I'll back up why I say it's the best. And don't get me wrong, I actually really like the delta regulator. And if I had to pick a second favorite one, it'd be the delta regulator. To be honest, it would be the delta regulator. However, why is Duff and Friends number 2 the best? Because you can calculate the highest loops in it.
Is that the best question mark or the best exclamation point?
Exclamation. It's the best for 2 reasons. One, you can calculate the highest number of loops in it, and that's just a practical fact. All 3 loop calculations of the TMD beam functions and the TMD saw function have been performed in Duff and Friends number 2 regulator. And that's just because it has very nice analytic properties. You can do it fit well with modern loop technology that people had developed to tackle other problems, like the Higgs total cross section. Now, the other reason why I like it is because it actually highlights a connection. And this is why I wrote down space-time. TMD anomalous dimensions, are the same in a precise sense as threshold. There's another type of resummation out there that's different from TMD resummation. It's called threshold resummation. Threshold resummation has to do with you have a hard scattering process and all final state radiation is solved. So all the energy gets sucked up into the hard scattering process. right? That's threshold. So you barely have enough energy in your collision to make whatever you want to make. And all final state radiation is perfectly solved. For a long time, people have thought about the relationship between TMD resummations and threshold resummation. How do you perform both at the same time? The reason why I like my particular last regulator is because it posits that there's a mother function, father function, parental function, the fully differential soft function, whose limits give you either all the quantities you would like to know for threshold resummation, or all the quantities you would like to know for TMD resummation. How does that happen? Well, I'm not going to go through the factorization, but if B perp equals 0, this is threshold. When n dot b equals n bar dot b equals 0, this is TMD. None are 0. Joint resummation, where you resum both TMD logs and threshold logs in some sense.
So you're at threshold and getting TMD resummation.
Yes, all from that mother function. So the proposal of Duff and Friends number 2, which is actually the regulator I'll be talking about. Duff and Friends number 2 is to treat these components right here.
I've got a question. In threshold resummation, do you have to deal with rapidity divergences the same way?
There are no rapidity versions.
That's what I think I did that once.
Yes.
So when we say the anomalous dimensions, I guess the mu equations are the same, but there's no analog of the Collins-Soper equation.
There's no analog of the Collins-Soper equation.
But
The
the
mu
mu-
equations are the same.
That I understand, yeah.
But here's the very powerful fact. If you're in a conformal theory, then not only is the mu equation the same, but the mu equation is conformally related to the Collins-Soper equation. So in a conformal theory, the two equations are actually identical. In other words, the rapidity anomalous dimension in a conformal theory is exactly the TMD anomalous dimension. So in other words, if I impose an extra constraint on the soft function that it's conformal, then the Collins-Soper kernel becomes identical to the threshold anomalous dimension. So that's what I mean by they're the same. They're actually the same. And why is this the case? Well, because you can get everything from the same function. And then when you apply additional symmetry upon that function, it relates to two quantities.
So
This is the reason why I like this regulator.
you have 2 minutes to tell us what it is.
So it's actually kind of obvious, right? What is the multipole expansion in the TMD? You set n bar dot b and n dot b to 0. So what should be your regulator? You expand about the limit that those two are 0. No, that's your regulator. And so that's what me and my friends, Wajing and Yili, proposed to be the TMD regulator. In the paper that we proposed it, we then did a toy 3-loop calculation to show that you can get some particular component of the rapidity anomalous dimension. And then since the people who can really actually calculate are Yili and Wajing, they went and actually calculated the full 3 loop.
Did you say a toy 3-loop calculation?
Yeah, it was n equals 4 superunions.
And you're
Only
working with
modern
what?
loop calculators think that n equals 4 superunit bills is a toy calculation, but it's actually easier there
And
because
Hodgkin thinks 3 loops is a toy calculation.
it's the reason why n equals 4 superunit mills is nice is because, and this is just interesting math, it has nothing to do with TMD physics. As you go higher up in your loop calculations, you can limit the space of functions that can appear in your loop calculation according to this notion called transcendentality. So a logarithm has a certain transcendentality. The integral of a logarithm has +1 transcendentality associated with it, so that'd be a dilogarithm. Then you can have trilogarithms, so on and so forth. As you go up in transcendentality, the space of functions expands, but it's finite at each order in transcendentality. Which means that if you can generate a finite set of data points about your loop interval that you want to do, then you can basically constrain the space of all possible functions, and from a finite number of calculations, guess the full basis and every single coefficient of that full basis. That's the idea, and that's what we propose to do in our paper. And this is called bootstrap. It's real nice because what we actually did is we did the threshold expansion, b perp equals 0. We expanded that. We knew how to do the 3-loop threshold intervals. And we just kept expanding around b perp equals 0. We went up to like 13 orders in the expansion. And that was actually sufficient to constrain the base of functions that are dependent on all components such that we could guess the entire function from just this expansion around b perp equals 0. And then once you know the full set of functions, you can then take the TMD limit where you keep b perp finite and you set these to 0. Just because you now analytically know. Am I out of time?
Yes, but you have something profound. We'd like to hear it.
I guess the last thing is about regulators. Is that regulators are not enough. To separate modes. You must have subtractions. Regulators will draw boundaries for you, but you may not draw them in the right place. So for instance, in the regulator, my space-time regulator, my exponential regulator, it nicely defines for you your soft function, right? And it draws boundaries for your soft function, and it forces your soft function to live in those boundaries. But you can ask, what is the boundary that it draws for the collinear sector? Well, it actually goes too far. It effectively draws a boundary down here, so that your collinear sector also includes the entirety of this offset.
And subtraction.
And then the same thing's going to happen on the other side. So the space-time regulator drew boundaries for me, but it drew them in the wrong place. It's fine for the soft function, but it's just not fine for the collinear functions. So we have to subtract any collinear function with my space-time regulator. And how I'm actually going to regulate it, I'm going to say that n dot b equals n bar dot b equals I b0 t. T is my regulated parameter, so we should always think of everything in the limit that T goes to 0. With this regulator in place, my true beam function, I have to deform its small momentum component, right? That's why I wrote that 0 there earlier. And I have to subtract out or divide out the entirety of the soft function because it includes in its soft region the entirety of the soft function. And you can see this order by order. Take your 1, 2, 3 loop diagrams, expand them in the soft region, the naive diagrams that you get out, expand them all in the soft region, and you'll just reproduce for yourself the exact soft function that you would calculate. Now, here's the interesting thing about this regulator. It is both the regulator, and after you've removed your divergences, it then becomes your renormalization parameter. But I may not have enough time to explain exactly how that works. I guess I'll just end there with subtractions. So no, I never actually made it to evolution. Because I never made it through the renormalization procedure, and I never made it through the RG procedure that then results.
That's okay, because we wrote 2 whole chapters in the TMD handbook explaining those 2 things. And thanks to your lecture, I think people will have a better understanding of what might be in there. Thank you, Duff. Allow a few minutes for questions.
I have
You can simultaneously grab coffee while we do that.
a quick thing.
Yeah.
If you go to the, where you write down the integral that you're actually dealing with over here, where it's like n per, sorry, just.
I can just rewrite it. So this interval?
No, actually, the final thing that you did right before you started talking about how to do the renormalization is easier. Let's see. Yes, that last thing.
Yeah.
So that could have equally have been d n dot p n dot p.
Yeah.
And so right there, that symmetry tells you, like in a sense, I feel like it indicates the fact that they both have to have some kind of equal footing.
Yes.
And in fact, it sort of leads this, right?
Yes.
Second thing, real quick, so with the collinear organization that overkills, the asymptotic part is right. That boundary is right. It's the one that overlaps into the softness pad. So it actually does a very good job on one side, but just not on the other.
Yes.
Therefore, this subtraction. The third thing is just because I'm so new to this, is that when you say using a new TMD regulator, even if people aren't using SCET, you're saying this regularization procedure can work for anybody using any method at that point.
Yeah.
Or would they have to build everything the way you do? Just, that's a very naive question. but-
No, you could take, say you could take Collins's soft function. And if you first did the deformation where you're sensitive to the other light components that I indicated. So you first do that deformation. Then you take his Wilson lines from being space-like to being light-like. Then you would have my soft function.
So pretty much
So
any
there's-
way of getting to your integral, you could somehow transform it pretty easily to make it so that this regularization procedure works.
Yes. The reason why this is ultimately going to be true is that both ways of doing things are going to reproduce the infrared exactly. So how you're organizing the infrared, that's the only thing that's changing. So all you're doing is, I mean, at the end of the day, all of the bare quantities are the same for each.
right? How you got to those bare quantities was a different thing. But at the end of the day, the bare quantities are the same. And then it's just a question of how do I regulate? How do I renormalize? And so in some sense, you can do the exact same procedure using all of Collins's language if you really want to. This really is just a question of now, I got this bare soft function, and even Collins would say that the bare soft function has no Wilson lines in it. It's just you have to deform it in some way to make it calculable, right? So then Collins chose his particular way of deforming it, which is probably the most terrible. I'm going to be honest. No one's done a two-loop calculation using Collins' soft function. And no one will.
And with that challenge, let's close the official session. So, but you can